All right, we were doing the actual beam deflections from last Friday. This is where, given some of our standard loads, we were able to figure out just, not just standard loads, but also standard supports. We looked at a couple, but whatever those loads happen to be, and we're going to show today that we can handle just about anything. Whatever those loads happen to be, we're going to be able to figure out what the deflection is, and that's actually finding out this deflection, the amount the beam actually moves due to the elastic response of the material itself. We were able to, for some simple loadings, figure out just what that equation was. Remember, that was called the elastic curve. Elastic meaning a couple things to us. One is the beam will, if not pushed too far, will return to its unloaded state if the loading is removed. But elastic also had to do with the fact that the curve was, this curve is continuous. Remember that term from calculus, well actually pre-calc, I guess you would even do continuous, where there's of course no step change in the position of the beam. The only way that could happen is, of course, if we had beam failure, and we're not stressing any of these beams to the point of failure. But it also meant that the slope was also continuous, meaning there was no abrupt change in the slope of the elastic curve itself. This meant that the beam had no sharp corners in it. Even if the beam itself was continuous, it can't maintain any sharp corners. There is a bit of a there is a way we could do that. I can't remember offhand if our book has any of these type of problems, but there were some in several other books where there are actually two beams joined together by a smooth pin joint, the very type we'd see in statics last fall. And these beams can, well, depending on whatever the load is, these beams can have a rather abrupt change in the slope of the elastic curve itself. I don't know if it'd do something like that, but it's the deal where there's a continuity in the beam itself, but a discontinuity in the slope of the beam because of this hinge joint. But like I said, I can't remember offhand if our book had any of those. So we worked through this, and it was usually a matter of figuring out the moment as a function of x, and then integrating backwards to this curve using the shear moment, the load, shear, moment, slope, and displacement curve, all related by their integration. Now all of these, not all of these, some very simple loads of these are all done in this Appendix C here, slopes and deflections of beams. And you can see some of the ones we actually even did in class. And what's available here is the slope usually as a function of the maximum slope, the maximum angle made by the beam under that particular load, or possibly the two different slopes at the different ends, depending upon what the load is. What you have to do, though, is be very, very careful. Don't use one of these solutions just because the problem kind of looks like the picture. It has to look exactly like the picture. It has to be precisely this case. The last curve is, or the last column is usually the beam curve itself, this curve that we were actually working on coming up with last Friday. Also available, though, are the deflection at a certain point. This is not the point of maximum deflection, it's just the deflection where the load happens to be. And that may be what you need. If this was a floor beam and this was a wall on that beam, you'd want to know the deflection right there, because it could deflect enough that the wall separates from its own ceiling above. You don't necessarily care what the maximum deflection is when it's more critical what the deflection is actually under that beam, under that particular point load. If you did need the maximum deflection, you can take this curve here, differentiate it, and set it to equal to 0 and find out where the maximum deflection is. There's some other possibilities. All the ones on this first page are those with simple supports, the pinned end and the roller end. Again, be careful that the loading is exactly as shown here, otherwise you can't use this. And all this is a matter of the author doing for these problems exactly what we did on Friday and then just giving you the results. You remember every time we need a moment of inertia, there's some very standard shapes available in the tables, pre-done for us. That's exactly what this is, some standard loadings, pre-done for us with the answers right here. On the second page were several examples of cantilever supports with different types of loadings on them. Again, you need exactly the loading shown in the picture to use this solution.
A lot of good test problems right there.
Oh, it gets even better, because there are lots of problems available that are not on here, but are relatively easy problems to do, and we'll talk about how we do those right now. So imagine we've got a simply supported beam with a uniform load, and remember that could be nothing more than the weight of the beam itself. That's exactly how the weight of the beam would show itself in one of these problems, as a uniform distribution of a load per unit length of beam. But then imagine we've also got a point load at about 1/4. So this is not the replacing the distributed load with an equivalent single load. This is a separate load to that shown by the uniform distribution. So it's an 8-meter beam, and that load is 1/4 of the way along. You'll remember one of the terms that appears very often in these, and you can see it all over the place on the chart here, this EI. That's the modulus elasticity, whatever the material of the beam is, determines that, and then I is the cross-sectional moment of inertia of the beam itself. So it's often worth it in these problems that it's either just given, or it's something, if you have the separate parts to it, that you go ahead and calculate it separately so that it's available for all the other times you need it. Sometimes this is termed the flexural rigidity of the beam, these two together. So we've got a beam with that already established. The first thing you should do is look in the tables and see if this solution's already available, and then you can determine what it is. Imagine we want to find the slope and the deflection at certain places. None of those are available. We're kind of close, but kind of close isn't good enough. If we tried to solve it with just this one, it wouldn't work. If we tried to solve it with just this one, it wouldn't work either. However, we can use superposition. We'll do an equivalent situation of two solutions superimposed over each other. That being the solution of just the single load added to the solution of the uniform load. Both of these are available separately in the tables. We'll get a solution of the two of them together by combining these two solutions as we go through these. So we can figure out the deflection due to the first loading added directly to the deflection of the second loading. We'll have the deflection of the two together. So we'll look at these. This one is the second one in Table C. In fact, is the one we did on Friday. We actually did a beam where the point load was 1/4 of the way along the beam. We actually did that on Friday. So we don't need to redo it because it's either right there available in your notes. The numbers might change slightly, or we can just take it right out of the table. So we're looking for the general beam deflection. So I gotta make sure I slip over to the right one. Be careful that you pay attention to what A and B stand for. So we have V equals minus P Bx over 6EIL, where L is the length of the beam and P is the magnitude of the point load itself. And then, which one am I looking at? L squared minus B squared minus X squared. And so we can put all of those values in, where for our particular setup, we have A equals 2 meters, B equals 6 meters, and L equals 8 meters. Oh, and P equals, 150 kilonewtons. So you put all those values in. We even have the EI. We can put everything in, and this all reduces down to minus 187.5 times 10 to the minus 6. 28 minus x squared. That's just reducing everything, putting all the values in, and collecting terms and simplifying. It all comes down to that. And that's the particular solution for just this sub part of the problem. And if we put in, let's pick a value, for example, right at x equals a, I think that's the value I put right at where P is. This comes out to be minus 9 millimeters. So we would know from this particular loading that that distance there is minus 9 millimeters. And if you remember, we do need them be very careful with the minus signs, because there are loadings where the beam could actually go above the neutral position rather than below. For the second loading, I'll have to bring it over here. Just, I don't have a lot of room there. The second loading is also in the book. It's the fourth one down in our book, as long as they didn't change the order between the versions. And so if we go over to this particular solution here, and then again we just fill in the pieces. Wx, remember x is the position, but W is that uniformly distributed load, the value of the uniformly distributed load, over 384. Let me make sure I'm looking at the right one. Oh, I wasn't. I had actually slipped down. 24 EI. It's hard when you can't see the whole picture on the screen. X cubed minus 2L x squared plus L cubed. And of course, we just set our values to what we were given in the problem. W is the 20 kilonewtons per meter. EI we've got. L, of course, is 8. And for that one, that's all we need to know. And then that, actually don't have it. Well, yeah, I do have it reduced. Just for simplification here. Not a bad idea. Oftentimes in problems, we need to look at a couple different points of these. And so it's nice to have it in a very simplified form. X cubed minus 16x squared plus 512. That's just all of the values we've got put in, simplified, reduced, cleaned up a little bit. And then at the very same place where x equals a, right under the load P, the value a doesn't have a specific importance in this loading we're doing now, but it relates to the original problem, so it's somewhat useful. So at x equals a, again the 2 meters in, we get a value of minus 7.6 millimeters. And so as this beam deflects at a point 2 millimeters in, we get a deflection of minus 7.66 for that separate problem. We add the two together, so V is the minus 9 minus the 7.6 millimeters is minus 16.6 millimeters for the entire problem. But just simple superposition. So we know this beam's going to deflect in some way, and at a particular point now, we know that the deflection will be minus 16.6. And we can also figure it out at any other place along there. If it was also important to figure out what these angles are, then we simply figure out the two angles on the separate sub-problems and then add them together. So rather straightforward, rather quick, as long as the sub-problems you need are available in the table, then you can save yourself a lot of trouble. If they're not, then you have to go through and figure out what the moment is as a function of x, integrate it to the slope, integrate it to the deflection, and finish the problem that way, just like we did on Friday when we first set these up. And if you go back to Friday's problem, you'll see that this specific solution is just like we came up with. Sorry?
No, execute enough.
Here?
Yeah.
Oh, what's missing is I had an x pulled out, and I didn't see it. I had it in there. So yeah, that would be there'd be 28x minus x cubed. Okay. good point. Got to be really careful with these subscripts, superscripts, and all the different factors and variables as part of it. Just for your own interest, you can notice that you'll get this very same 9 millimeters if you do it from the other end of the beam, where A now is 6, B is 2, L is still 8. You'll still get the minus 9 millimeters now at a point 6 meters from 0, just to show you that you can use that from either end, but you have to be very careful which end, and that you make sure that the values you put in match the pictures there precisely. Okay, so we'll do a couple more. These work well with some examples. So here's a model of a hairbrush design. So it's a long plastic beam that the user's going to hold on one end with a fist and then pull down blonde. So I'm using yellow. There's your hair. Pulling the hairbrush down through the blonde hair, and we'll make a model out of that as a beam like this, where we'll model that end as cantilevered, as it would be as the user is holding it, then with a uniform load, and we'll take it to about halfway. So that'll be our model, and then we'll put some values to it. Oh dear, what do I mean by that number? Let me check L. Okay. So the entire length is 120 millimeters. This is half of it, goes half the length, so this is 60 millimeters across there, and the load is something like, oh, did I put 50 or 60? Oh, I gotta stop doing these things late at night. The load 50 newtons per meter, with a proposed cross-section of the hairbrush. Make it out of plastic, some kind of unreinforced plastic, so we'll have an E for it. And I said 10 millimeters by 25 millimeters. And plastic has a modulus of elasticity of 2 gigapascals. So E times I is something like, oh, I don't know. Oh, I didn't do it separately. So you can do it separately. Remember to watch your units, and I for a rectangular shape is just 1/12 BH cubed. So we know we're going to need that. I just didn't happen to have it on my paper. First thing to do is check to see if this solution is in the tables. If not, we've got to come up with a solution that represents it. So looking at the cantilever solutions, well, there's a uniform load. There's a uniform load halfway across the beam, but it's at the cantilevered end, not at the free end. So we can't use that solution. So we don't have an available solution in there, but we can make an equivalent picture of it that will suffice. So here's our original model. And we'll make an equivalent model out of it of the one that is in the picture, which is this one here. That is in the table, and the uniformly distributed load goes to the halfway point, which is sort of like what we've got, and then we'll add to it the uniform distribution that's also in the tables of the same magnitude, but going in the opposite direction. That way, this first portion here will cancel that portion there to leave the first part of the beam unloaded, which is like in our model for the hairbrush. And then we'll have a load here, it'll be in the opposite direction, but we'll just have to be careful. Remember the hairbrush, it doesn't matter which way you're going, you have to do it both ways. We just have to make sure we get it so it makes sense for the picture we've got here. So, I guess, let's make it so it is better. So it does better match. We should put this one upside down. That makes more sense. Right, David?
Yeah, that's what
I can see you frowning. We'll make this one then like that. Not, that'll match our model precisely. Again, these two ends will negate each other, leaving it unloaded. Then this adds to the unloaded end and gives us just exactly what our model is. So you can do that. Find. Let's step through it. Find the deflection and the maximum angle. We know it's going to do something like that. The maximum angle we expect to be down there, and we also expect that's where the maximum deflection will be as well. So practice opening up. If you have your book, that'll help. If not, I'll put up the relevant ones right here. Yeah, I can get them, just barely get them both on the screen. No, I can't. There we go. Stay. Okay. So we'll need this one, and then we'll need the first and the third here on the pages that we've got. So you set those up, see what we get with them.
The third you just make positive.
Sorry? Yeah, well, for this one,
Positive.
yeah, you'll have to make, well, W, remember, is positive when down, so you'll have to put in W as negative, or just change these to positive and put in the magnitudes. Either way, all the same. Same with the deflection. These are all assuming downward loads, so all of these deflections are negative, and the angles are even negative too, as shown. All right, so see what you can do with putting those two together. Just so I don't get sidetracked from my notes, we'll number this one 2 and that one 1 as we refer to these, because you'll need perhaps V1 and V2 as symbols. And we can also figure out the elastic curve as well. So there's the 2 solutions we need in the table. Let's practice and see if we all get the same thing. You're looking at the same ones? Looks like it. You're the international edition too? I'll have to remember that for the test. Otherwise I'll be pestering you all day. Okay, so again, set up the curves with the appropriate values, and then just add them together for the 2 superimposed solutions. We've done this superposition thing before. And you can imagine some of them can involve 3, 4 more of the simple models added together. Phil, looks okay? Look at that death bridge this person has on their airbrush.
Why'd the thumb go?
The thumb is it's along the back side there.
Okay, let's go with that.
Like that, is that okay? David, you happy with that? Much better now. Now you can finish the problem. I guess we could argue whether the cantilever should have started right back here, but we didn't have a solution that would work for that. So we need to simplify a little bit. What?
You change the sign?
I didn't do that one, so I should have did that.
Did you get answer? Sign yours?
No, I didn't do that.
Okay, so for what I've called number 2 here, remember we're looking for the deflection at the far end, and they're going to be different. There's different equations there because there's different loadings there. So we're looking for the loading at the far end. Yep. So V2, if we're looking for the maximum deflection out here at the free end, that's the second of these 2 equations. It's inverted, so we take off the minus sign. W over L cubed instead of minus W over L cubed. 192 EI 4x minus L over 2. And I believe we've got all those values.
What
And
did you
then,
get for EI then?
I don't happen to have EI out separately. I do have I.
26. Yeah. 26.
Well, not 26 even.
With 0.4.
20. Well, let's see. 2 times 10 to the 6th newtons per meter squared, and for 1/12 BH cubed, I got 1.28 times 10 to the -8 meters to the 4th.
Is it 10 to the 6th? 10 to 9.
You have GPA.
Yeah.
Oh, yeah. Yeah, I was doing megapascals, so. So that's times 10 to the 9th. So whatever that comes out to be, I just don't have it calculated separately. And then the maximum deflection. Again, take out the minus, L cubed, and remember all these units should work out. Did the units work out?
Everything's.
You hope so, since you didn't track them. You're better at doing them in your head than I am, David, that's for sure. And then for the second one, we can use the loading just as shown. Minus WX squared, 24 EI. And then the polynomial part, x squared minus 4LX plus 6L squared. And the maximum expected deflection, the angle, the slope, again at the end, and again the model and the solution match each other, so we can use it just as pictured.
And for X, we're just doing it halfway point,
X is,
right? Halfway.
no, X is where along the beam you're interested in this. So if we want to know what the maximum deflection is,
Oh, we want to pull it.
you'd want to X at L.
Sorry.
If you want to know it anywhere else in between,
So multiply this by 2.
carefully reduce everything. Check your units, make sure everything's in meters if that's what you're doing, all those distances in. People get some numbers. Travis, you got some numbers? Matthew, you? Units? No, units is always right. U2, no units. U2, no units. How can I tell if your numbers are right? What?
So the units cancel.
Radians.
Right, Kristen, Phil.
I don't have all the intermediate values written down, so.
Total. 0.06.
With x equal to L on all of these, a lot of it simplifies. You can really get it reduced down to a single piece there once you get all the numbers put in, so. See if we all agree.
What are the chances?
You can imagine if airbrush was too flexible, it wouldn't feel quite right.
Maybe a little flexible.
Yeah, a little bit,
Flex brush.
especially if you're worried about actually losing hair, which none of you are yet. But you will be. I'll see you guys at the 50th reunion.
Never.
We'll be laughing at how bald and fat we are. Isn't that good? You'll be laughing at us. You're laughing at us already. It's just gonna get worse. Okay. All right, everybody's coming along. Who's got some values? If you think you got them, ask somebody else who does. You can compare them.
So we get this in radian? Oh, it's so small, it doesn't matter.
Yeah, remember, this is all based upon the angles being very small, the tangent theta equals theta. Yeah, we had to use that from the very first, almost the very first moment when we started going on, got going on. All right. So yeah, these are not typically very big deflections that we're talking about. Plus, this is not a very large object anyway, so it doesn't have a whole lot of length to flex. So the deflection, both the angle and the absolute deflection are going to be small. Get your plus and minus signs right, because these two deflections are in opposite directions.
Oops. Right. Yeah, we screwed up.
The minus sign in there has to do with a positive load, which we have always taken to be a downward load as positive.
0.22.
Small?
Pretty small. Small.
Is that meters?
Millimeters.
Millimeters. He's got 0.02 millimeters. But that's minus.
Yeah.
So 1 was down, 2 was even downer?
No, wait, this
No,
is
no.
minus, this is
Yeah, something didn't quite work there.
good, right?
Because we expect there to be a negative displacement as pictured.
Take this one.
Yeah, Newton meter squared over Newton meter squared, once you fix that, which is no units, but remember that's when radians applies. Yeah, well, that's gotta be 10 to the 6th newtons, so that's that newtons. Tom, got anything yet? Both positive? Bless you. Because that's a positive deflection. This is a negative deflection, and our model, we'd expect it to be,
Oh, I only have number 2.
Oh,
It's
okay.
not complete.
okay, yeah, number 2, we expect to have should be positive. And 1 should be negative, and hopefully if they work out, the total deflection is negative. Is that negative? EMF be positive? I guess if the brush being pulled down would give it an upward load on our original model, but
Name of the total deflection?
this is the Australian real color here, so it's
Okay,
negative.
-0.012.
Oh, I get what you mean.
For what?
Yeah, she's pulling down.
Negative
The uniform that should be
0.012.
low would be up.
Millimeter,
What'd you get?
-1.1.
1.1. What'd you get?
Phil, what do you have?
Negative 0.77 millimeters.
But it is negative for the total.
Yeah, I got
For the
it.
total. And you got 0.77 millimeters,
0.012.
0.012.
0.004.
Oh, that's closer to what I had. I had 0.004.
I had 0.4.
Yeah, you're all wrong.
That's meters,
Millimeters.
millimeters. Oh, I had 0.004
You get the individual numbers?
centimeters. No, I don't happen to have the individual numbers.
You got negative 4.3 times 10 to the negative 5 meters.
Yeah, so one or the others may have slipped a power of 10. What'd you have, David?
10 times, probably around, almost exactly 10 times what you had.
But it was negative?
Yes.
Okay. So did you have the same thing then that Travis had,
What's your magnitude?
but not negative, you had positive? Okay. All right, well, that's details. The physics is there,
Yes.
just perhaps the 6th grade algebra isn't for either one of us. I was kind of rushing through this last night.
Well, we did this last night.
Yeah, which is, the tail end of the long weekend.
Of hard drinking.
No, no, easy, easy.
Wonderful. That's
All
what
right.
I do think that
So
lasts.
we'll double check those numbers when you've got a couple minutes to now. But the basic idea is there. I want to have time to get on to the other application of this as we've seen before. So, as long as your physics are there, which the simple superposition works very well in lots of different applications.
0.003.
All right. We also have used this type of thing for those problems that are statically indeterminate. We did this for torsion. We did it for the strain, simple elongation. And we can do it now for the beam deflections. So imagine we have an over-constrained beam. What that means is a beam for whom the simple statics equations we've used before are insufficient. If we have a beam like this, our typical static solution from last fall will not suffice. There's just too many unknowns for the number of equations we've got. But we've now got this idea of superposition to add on as another possible, or actually counts as another equation, and another equation actually comes into it. So we can make this into two models. This one, of course, isn't on the solution, so we can take it as two models that will superimpose and use that as a way for us to then get to a solution that we do have. This solution is available. It's the one we just looked at. That will cause a deflection of something like that. We expect the beam to deflect something like that. Remember, a cantilever support, the slope is 0, and then there's 0 displacement over here, so we'd expect something as a displacement like that. So we can't clearly get it with the solution we've got there, but we can add to it another solution that we do have available, and that's then a simple load at the end that brings the beam back up to where it would have been, such that those two together we would expect to give us the solution we have there, and that will give us the reaction at both walls. So maybe we'd say something like this. We'd have a V1 down, and then with the second model, the same magnitude deflection only would be up, such that the two added together means no deflection at the simply supported end. The 0 slope for both will guarantee 0 slope for the other solution, and we'll then be able to find the full solution. So let's put that together. From Appendix C, we have V max as minus WL fourth 8 over EI. So that's going to be our V1. And the minus is appropriate because our model matches that in the book. So we know we expect a maximum deflection at the end of that particular model of minus WL 8EI. And I don't happen to have values for these, we're just doing them in absolute variables. And then we add to it the inverse of that top loading. So again, we're using the first and the third, but we've got to flip the first one over because it's in the opposite direction that we're using it here. So that will be, take out the minus sign, PL cubed over 3I. All right, that's this deflection here, the maximum deflection of a single point load at the end of the free end of a cantilever beam. And then we're saying that, maybe I'll call this a 2 here, would make more sense. We're saying that V1 plus V2 equals 0. That, as simple as it is the extra equation we need to solve the original problem. And so we can then use that to solve for P, which is equivalent to the reaction at that point, which is 3/8 WL. As simple as that. When you put V1 plus V2 equals 0, put those two together, the unknown is P that we're using to represent the reaction at that end. However, you're not done, because we don't have the reaction at the wall. We also need that. So that is going to take a separate model to find the reaction at the wall. So we'll split that into two models as well. One of them will be a simply supported beam. Actually, we're going to have to model this twice. So, a simply supported beam. However, we know that this one would have a slope at the left end, which we don't want, so we'll have to find what moment is there that will bring that back up. So that's actually itself two models, both of which we can do to get the original anticipated deflection. Not in any particular order. We can do a uniform load distribution that'll give us deflection like that. Add to it a simple moment as calculated by that, and then we can use the two together to give us zero angle at the wall such that theta 1 and theta 2 are equal and opposite.
Why do you need those?
We need those two to find out what the reaction at the wall is. For any of our static solutions, when it says find the reactions, it's not just at the support, the simple supports, but also at the wall support.
Right, so you know P on the far right, so why do you need two separate models there?
Because we don't have any simple model we can use to illustrate that one. Well, I guess we could. We could have made this as another solution. We could have done it as this. Well, actually, it's the same two we've got there. Well, no, it wouldn't be, because
P's all the way down on the other side.
yeah, if we did this, we're not going to get the moment at the wall. So this isn't going to suffice. We had to bring the moment into it, so we had to remodel it and then split that into the superposition. So now we're back on the other page. We're using this load here plus this load here, only done from the different end with the moment running in a different direction. So you again have to be very careful with this. We're using these two middle loads, and we're using the angle ones. So there's the ones we're using there. Okay, so we have to be a little bit careful. I'll call that 1 and that 2, just to stay consistent with my notes. So, the first one you have to be careful with the subscripts. We're doing the angle over at the end where the moment is, so we want this particular picture. I have it listed as MA. MAL over 3 EI. And as pictured, that will be positive. So if the moment's positive, then this will be in the correct direction. Because both the sides are swapped and the moment's swapped, that's like two negatives, so we can use the same equation. Actually, I don't want this as theta max. Just theta 2. And theta 1, it doesn't matter which end we use because it's symmetric, so it's minus L cubed over 24 EI. Minus WL cubed over 24 EI. Did I read that right? Minus WL cubed, yeah.
Do you theta 1 and 2 reverse?
Yeah. I want to change. Yeah, these numbers are right. So I want 1 here, 2 there, 1 here, 2 there. So 1's on the bottom. It's arbitrary, remember, it's just the way I happen to do it in the notes. And so we put that together, we should get an MA equal to minus WL squared over 8. Remember, every time we did this superposition thing to do statically indeterminate problems, the material itself didn't matter. It ended up canceling out. And that, again, is the case. When we put these two things together, theta 1 plus theta 2 equals 0. Solve for MA. Not only the material, but the cross-section of the beam cancels out.
Should that be positive? Theta 1 plus theta 2 equals 0. The negatives can be cancelled.
Theta 1 plus theta 2. Yeah, that's a negative. No, that's our negative convention. It should be negative. So does it not come out in the algebra?
Depends on
We got MAL over 3EI minus, because I have a minus here, WL cubed over 24 EI. And those two have got to add to 0.
Right, and then we move the WL cubed over, it's positive. So the negative goes away.
Okay. Yeah, you're right, because we don't need this in a negative sense. We've already got the proper sense to it. So, yeah, this would be a positive then. All we need is the magnitude. We already know the direction. We already know the direction of a moment at a cantilever wall. Now, the question might be, we use two different models here. We use this model first, where we have the uniform load with a point load back up on a cantilever beam. Then we use this model, a simply supported uniform load, and a simply supported beam with a moment. The question might be, we use those for two separate purposes. We use this for the right end reaction, we use that for the left end reaction. The question might be, do these two models give the same elastic curve? we have an elastic curve that we'll get from this solution. We'll have an elastic curve we'll get from this solution. The question is, do they each give the same elastic curve? If they don't, then it might not be appropriate to choose two separate models. So let's let you three find the elastic curve for this model, and you four find the elastic curve for this model. And we'll see if they're equal. If they're not, then you either have to decide is one the better model than the other, or perhaps neither model's good. And it may not be obvious which is which. So do the same thing.
What's the load?
Just use P and W for the loads. That's W, that's P. Actually, we just need W. So find the elastic curve for the two, which is a matter of, well, for the one that's pictured up there, which is the second one we did, you've got this elastic curve over here. You just need to add those two together. Taking into account one of them is upside down. And then for the other one, we use those two cantilever solutions there. For those elastic curves. So let me squeeze this in someplace. Thanks, Joe. Okay, either group needs to see the elastic curves. People doing the left-hand one, your elastic curves are up there. Don't forget that we've got the simple load at the end of a cantilever beam upside down. What do you mean, Joe?
P equals.
For your two beams, that's these two right here. You've got this load with this elastic curve, and then this load with that elastic curve. Be careful that this is at the opposite end from which X is. On this one, for you people where the moment is actually in there, use the, I erased it. Use the one we solved for. That m equals WL squared over 8. Because we now know that. So
take out the minus sign? Since it's
Yep.
deflecting down.
Yep.
Okay.
Can you put back?
This one? Yeah, let's see, it's the first and the third there.
Does that seem? Does it depend in terms of variables or?
Yeah.
Okay, again, just write out the equation for the elastic curve and put them together. Let's see, I have this one on the board. So. Right there, minus wx squared. The minus is okay, we're in the same way, 24 EI. Now the the EI is not going to cancel in this case. Adding these together, but they don't add together to equal 0. They add together to equal whatever they equal. X squared minus 4LX plus 6L squared is the first part. Yep, that looks good. And then we add to it this one. Where we now know the load. Any convincing, I think I wrote down. Yeah, we know the load P as well. That's got P in it, but we know what P is. We know that it's 3/8, whatever, 3/8 WL. So we can put that in, but it's upside down. Where P equals what we found before. I don't have it written there. It's 3/8 WL. So that'll give you a load curve. The elastic curve for one of them, and then for the other one. We have to go to this one, the second one, where we use that equation. Which one is that? That's the uniform one here. It's in the proper orientation. X cubed, well, minus 2LX squared plus L cubed. And then V2 is the second one with the moment. This is upside down, so we have to turn this over. We know the magnitude of M0. I had an MA on the board, so you can figure out what that is as well. Using the moment we now know. No minus sign there, because that one is upside down. L squared minus x squared. And those should give the same elastic curve. You guys have yours to compare as a group?
This is like a good short little program would be better than those types of things. Put your variables and have a slider function where you can.
Yeah,
start-
possibly. And you can imagine, there are other solutions for these. For example, we've got this L over 2, but what if it's just L as some variable of x? So, other books have other solutions. So hopefully this works out. Now add those together.
What happened to keep
These two, add those two together to give the complete elastic curve. And that should equal these, the ones these two are adding together, this group's adding together for this elastic curve. It should give the same elastic curve. Assuming you've got the same. You gotta hurry, we're running in overtime. I help you now, it's $100 an hour. All right, we're at the end there, so I'll put it up.
Who knows? You know what's cool about
As a function of x, it should look like wx squared over 24 EI. And then depending on which one you put first and what you do with your algebra, 5/2 LX minus 3/2 L squared plus, no, minus x squared. Did you guys get that? Make sure I'm reading the right one. Wx squared over 24 EI, 5/2 Lx minus 3/2 L squared minus x squared. And I got that the two did give the same model. If yours doesn't agree, it's most likely just algebra. The physics is nothing more than writing down the two equations and adding them together. That's all the physics is. So, did any of you agree?
You got some of the terms.
Got some of the terms.
Hey,
All right.
80%.
Double check that, see if you got them all. But they do give the same elastic curve, so they're both legitimate models. Luckily.
Aren't they supposed to be the same?
What?
Always? Will they always be the same now? Do you do it right?
Yeah, I don't know why they wouldn't, as long as you do it right. Easier said than done though.